a lot of notes, a lot of you listening to me. We're going to look at first chapter 1, getting started, part B. And we're going to look at, first thing we're going to look at is what are called sampling methods. So sampling is where you typically, instead of asking everybody in the population, you try and ask as large as you can afford, a smaller representative group of people from the population. And there are 5 main methods. There are lots of others, but these are 5 of the main methods that we use in statistics to get those samples. And they're called a simple random sample, a stratified sample, a systematic one, a cluster one, and lastly, a convenience sample. Now, there are lots more, but these are the 5 we're going to focus on mostly. So let's begin by introducing you to some terms that we will be using. The first term is called the sampling frame. Now, the sampling frame basically describes the people that you're going to pick in your sample. Now, ideally, that should be the entire population. So your sampling frame should be the entire population. That would be the best scenario. But there are lots of reasons why that doesn't always happen. Some are very practical. I mean, if I went and said to you right now, I want you to ask every single person who's in America their age. Wouldn't that just be impractical? Well, for starters, we don't know who everybody in America is right now, right? Aren't there some people that are unknown to us? And secondly, I don't know where they all live, right? It'd be quite hard. And all sorts of other, can you just imagine how difficult it is, right? To ask everybody, or even to ask 1/10 of them, right? Randomly pick 10% of Americans and ask them their age. It's not really going to be very easy to do, but we try if we can to make that happen. And so your sampling frame should really contain all the people in the population, but very often it doesn't. Sometimes, for whatever reason, your sampling frame only can be chosen, the people you choose are from a subgroup of the population. So, for example, suppose we wanted to know how many cars were owned by families who live in Bremerton, right? So we want to know, a typical family in America in Bremerton own on average 1.2 cars, right? Or 3 cars, whatever it might be. And so we approached that by getting a sample. And the sample we're going to use is we asked 1,000 people, and we did it by just phoning them. So we got a hold of an old telephone directory kind of thing and just picked randomly 1,000 people and phoned them up and said, hi, how many cars are in your family, right? How many are parked, in your driveway right now, kind of thing. And we would collect our data. Now, the population should have been all the families in Bremerton. But our sampling space is actually only people who had a phone that we could contact, right? Because the only way my sample was made up of people I phoned, right? Now, that means I'll never ask someone who doesn't have a phone, right? Secondly, I won't ask or be able to ask at least. Do you know you can have X directory, at least that's what we call in Britain. Do you know how you can just have your number removed so nobody knows what it is? You can do that in America, can't you? You can go X directory, whatever it's called here. Do you know what I'm talking about? Yeah. So I'd never phoned in, right? So there is the problem. My sampling space only are people with phones. Why could that be important? Well, here's an assumption that may be valid. If you don't own a phone, isn't the chances one of the reasons is you're poor? I just can't afford, it's $400 for a cell phone and, $50 a month. I ain't got that kind of money, right? Would you agree that people who are that poor probably don't have many cars? Probably. Do you see how my estimate is going to be distorted because of that? So if you have a sampling frame that isn't the population, you have to be aware that it could cause problems, right? Your data might not be as good as it could be. Now, let's return to our list of 5. Hopefully you can watch this video and write down all the descriptions later, because if you frantically write everything I'm doing right now, it probably won't help you, because, well, me, I can't write and listen and read at the same time. There are just too many things. I'm not good at multitasking. So let's do the first one. A simple random sample is the ultimate sample. It's the best sample in the universe. That's what statisticians love, if they can make it happen. How do you describe what a simple random sample is? It's a sample where every single person in the population could be picked and they all have an equal chance of being chosen. Right. That would be perfect. An example of that might be you choose, say, 1,000 people from the voters list. Of Bremerton. And then you ask them who they would vote for. Now, if we analyse this, I am interested in who they're going to vote for in the next general election, right? The next presidential election. I'm going to get a list of every single voter in Bremerton. That list exists, right? It's called the voters list. Mostly it's up to date, right? Some people die, some people leave, some people come, but mostly it's up to date. If you randomly pick 1,000 people from that list, aren't you picking, your population here is voters, right? So that's perfect. You can just go to your computer and say, here's 20,000 people that can vote in Bremerton, pick 1,000 of them, and the computer will just randomly pick 1,000 people. And then you have to go and hunt for them and find out where they live and ask them. That would be a perfect example of a simple random sample. If I wanted to do a simple random sample on, I don't know, what the voting preferences of Olympic College students are, couldn't I just simply get a list of all our students that exists? And then couldn't I just randomly pick 500 of you and ask you, who are you going to vote for? And by the way, none of you answer that question. It's none of my business. Right? But if I did, I'd say, who are you going to vote for? And you tell me. Second one on our list is a lot more details. Wow. It's called a stratified sample. Now, this sample is one where you split the population into groups called strata by some common characteristic of them. And you normally split it into at least 2 of these groups, 2 of these strata. And then you pick a simple random sample of a certain size is going to be chosen from each group. So that's quite convoluted. And the size of each group depends on the percentage of that group in the population. So let's see how that works. Suppose you want to find out about people's voting preferences in the next election. And there are 2 main stratas that you're interested in, a male voter or a female voter. And next, there are young people, which you're describing as 30 or less than 30, and older people that you're going to describe as 30 or more. So if you put that together, right, are you a male or a female? Are you old or young? Do you see how that breaks into 4 groups? And you know, because the census, that 18% of Bremerton are young males, 30% are old males, 20% of Bremerton, we're talking about voters here, are young females, and 30% are older females. And what you then do is, let's suppose you're going to ask a sample of 9,000 voters. You split them up as 18%, 30% of this number, 20% of this number and 30%. In other words, you go find 1,620 males that are young and ask them who are going to vote for. And another 2,700 older males, 1,800 younger females, and finally 2,700 older females. And you do sample, essentially, don't you do 4 samples? You go find young males, 1,620 of them, say, who are you going to vote for? Right, and so on through these groups. Now, this is quite a complicated process, but this is actually very common. Simple random samples are just really hard to do. Don't you have to know everybody in Bremerton, right? Every single one of them, right? And you have to randomly pick them. They very often do this because it gives them more details. So can you imagine that you're a Republican and you paid for this research and it came and it told you you're doing really good with the old males and the young females, but you're not doing so good with the older females and you're definitely doing really bad with the younger males. Now, that kind of extra detail is very important to politicians. Can you see? Because they can say, okay, why are we not getting to the younger males? I want to try and get their vote. You know, what is it, blah, blah. And they are continually doing that. There are whole groups of people who work for political parties, and their entire job is to collect this data, analyze it, come up with some reasons for it, and then try and figure out how they're going to improve their candidate's opportunity to win. Now, since I don't like politicians, this is my version of that. Suppose you are in an area and you find out that you're doing really badly on the young females. And you think, why is that happening? And the guys go into it and they say, well, you know, the young females are quite pro-abortion. And your stand is totally against it. Strangely enough, it's not unheard of for politicians to change their opinion. And suddenly you become a pro-abortion candidate. And you might lose some of these, but if you gain more of these, isn't that the net effect? You've improved your chances of getting elected. Right? So don't be surprised that politicians, in my opinion, only believe half the stuff they tell you they're in favour of. And the reason they choose the half the stuff that they tell you they're in favour of is because someone else has told them that if you have these opinions, more people will vote for you. Now, does that sound cynical or realistic to you? But that's kind of what they do. And they know what to do because of this type of sampling technique. Now, the next one is a systematic sample. And what does that do? Well, if you can take your population and put them into some kind of order, you randomly choose somebody to start with, and then you choose the next individual by picking the person that's key positions after that person. So what does that look like? Suppose you wanted to know the percentage of high school students who drive a car to school. So your population is high school students in your school. And you don't want to ask all of them because it takes too long. Well, you could get a list of all your students and couldn't you put them in alphabetical order? Wouldn't that be a really so Aaron Aardvark is first, right? And Zach Zebediah is last, right? And you randomly pick the third student, right? Andrew Aaron, whatever his name is, right? And then you pick the 13th student. So you imagine you're getting a big list. Oh, there's Andrew. 13th guy, 23rd person, 33rd, 4th, all the way to the end. Do you see that what you're doing there is only picking 10% of the entire population, right? All students, right? Because you're only picking every 10th one, right? 3, 13, 23. But in a lot of ways, isn't that probably going to be a pretty good sample? Plus, it's relatively easy to do. Next sample is much more messy. And this one is done by governments a lot. They seem to like this particular sampling method. They do it a lot. So what they do in a cluster sample is you break the population into what they call clusters, and then you randomly choose a few of these clusters. And then the trick is you ask all of the people in a particular cluster, whatever it is you're interested in. So let's see how this might work. Suppose you're interested in the opinions of doctors who work in hospitals about abortion, right? You want to know if they're in favour of it, against it, or, 50-50, they're not really sure. If you were doing that through a cluster sample, what you would do is your clusters would be individual hospitals in the United States of America, right? Let's suppose there's 1,200 hospitals in America, right? Probably more, but let's pretend there's 1,200, right? Couldn't you get a list? The government has a list of everything, right? Couldn't you find a list of every one of the hospitals in America, right? 1,200 of them. And they randomly just pick 200 of them. Right? So that hospital in Arkansas and this one in Kansas and so on, right? They pick 200 at random. You then go to those 200 hospitals and you ask every single doctor who works there, right? So there's no some of you pick and some of you don't. You ask every one of those doctors in each of those 200 hospitals their opinion on abortion. And that is called a cluster sample. For instance, couldn't the clusters be the 50 states in America? And then you randomly pick 3 of those states, right? And then you find out how much money they're worth, right? And that gives the government a little snapshot of how the country is doing. Right? Cluster sample. Last one, convenience sample. The worst, hopeless, never should use it sample, but it's here because far too many people use it. And I want you to be aware that convenience samples are horrible. The reason they're horrible is that they are fraught with the opportunity to get bad data. They're fraught with bias. The sample is just got one thing. It's easy to collect. That's the only reason you would do it, right? You don't need to put a lot of thought into it, right? You don't need to collect a whole load of information about the people before you even decide who you're going to pick. You just turn up and ask some people, right? Pretty much anywhere you like would be a convenience sample. So we're interested in voters' opinion in raising school levies in a city, right? So let's say Boston wants to, add an extra 2% to, property tax to pay for school improvements, whatever it is, right? That's what you're interested in. And the way they do it, the sample, we collect our sample by just going to a local mall at 1 p.m. in the afternoon in a wealthy part of the city and just randomly ask people as they walk by, are you in favour of an extra 2% onto property taxes to pay for school improvements, Now, can you see that's a very simple way to collect data, right? Don't you just find a mall somewhere, turn up? Have you ever had it? Kind of a little clipboard, pen? Excuse me, ma'am. Just want to ask you a couple of questions here, and then blah, 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 right? That kind of thing. Now, just think of the problems with that. The sampling frame is definitely not all the people that you should have in your population. Aren't your population here people who pay property taxes, right? Because they're the ones that are going to pay for it. What would you be missing if you went to a mall at 1 p.m. in a wealthy part of the city? What kind of people are you probably not going to be asking?
You're missing like a whole nother demographic, probably like poor people, since it's the wealthier part of town.
Okay, people who haven't a job or don't need a job, they're going to be at the mall, right?
Yep.
You probably won't be at the mall because you're probably still doing your schoolwork, right? So all sorts of people are never going to be asked, or very few of them are going to be asked. Can you see then that your data could be quite heavily skewed to whatever kind of people go to that mall at that particular time of day? and they may not be a good reflection of all the population that you're interested in. Yet convenience samples are used far too often. Right, picking politicians, because I like to pick them. Have you ever heard of a politician or two different politicians who said, we conducted a poll and we found out that the majority of people are in favour of tax cuts? And the other politician said, we conducted a poll and we found the majority of people are totally against tax cuts, right? Now, how can you be both at the same time, right? One of them's the truth, right? Probably, right? One is true and one is not true. Well, isn't it because each of them probably did a convenience sample? Now, if you want to get the right answer, don't you ask the people that you want to ask, that you know are likely to give you the answer you want, right? So can't you pick your sample in such a way that conservative people will pick a sample that has more conservative people in it, right? And Democrat people will do exactly the same thing. So politicians should, and polls should be totally ignored. I don't care what they tell you, just ignore them. They're really there to influence you. They're not really telling you the truth, because I'm 99% sure that they're not doing a simple random sample. They're doing a convenience sample or something even worse than that, right? A deliberately biased sample. So that would be my advice, totally ignore them. Another reason they do it, and I think I'll tell it now before I forget, is there is a way of cheating, that's the right word, I think it's cheating, which is called voter suppression methods. And here's a good example of how a voter suppression method works. The day before an election, you put out a poll and you say that your candidate is 25% in front of the other guy. It doesn't need to be true, probably isn't, but you put that out there. Now, how does that do voter suppression? If you, let's say it was a Democrat that said it, right? Our candidate is 25% ahead of the Republican candidate, right, for the governorship. The way that suppresses votes is, if you're a Republican, you're probably going to say, what's the bother? Why should I go out? My guy's not going to win. It's a waste of time. Now, does that affect everyone? No. But couldn't it affect 3, 4, 5, or 6% of people who were kind of not that keen in voting anyway, and it gives them an excuse not to vote? Couldn't that 3, 4, or 5% actually have the effect of the Democrat guy winning them? If all the Republicans who were going to go out and vote actually did go out and vote, wouldn't your Republican guy could win? Can you see how that is a very sneaky way of cheating? Right? Voter suppression. Now, it's technically not illegal, because couldn't you make sure that you asked the right people when you did your sample, right? You deliberately picked a bad sample. So watch out for anybody telling you that your candidate has got no chance of winning. I don't care who your candidate is, Republican or Democrat. Just ignore that evidence, if they call it. Just vote. Vote for whoever you're going to vote for, and, you know, let it sort itself out later. Politicians are not very nice people when it comes to power. So I basically distrust the little darlings. So let's show you some of these questions, because they are basically, a lot of them are, here's the thing, pick some answers. So who shall I pick here? Okay. First, are you looking at some questions? Yeah, okay. So number one, a researcher wants to study the use of public transportation in a city and obtained a list of riders who registered for a mobile app. The researcher randomly selects the number 9 from a table of random numbers, and then they choose every 9th rider. Right, so you imagine they've got a big list in alphabetical order, right? And they picked number 9, number 18, number 27. From that description, which of these 4 guys are we talking about?
Is it the systematic random sampling?
You see, it's got the features that make it systematic, right? You picked a guy and then you picked every 9th guy. An investigator, this is number 2, conducted a statewide survey to determine the smoking behaviour of high school students. First, he divides the schools into the states, into groups based on school districts. Next, the investigator draws a random sample. So he did states, right? That was his first group, and then within each state he picked, you know, Kitsap and whatever district, whatever school districts are organized. And let's see. And next, draws a random sample of students. Now it's a random sample of students. He doesn't ask all of them, right? So it's
Stratified random.
Yes. Now, what's the difference? If it was a cluster, wouldn't you have to ask every single child in that school district, right? Every single doctor in that hospital. But if they only ask a sample of it, you see that makes it a little bit different. Okay, number 3, an outdoor clothing manufacturer wants to understand the purchasing behavior of people with different recreational hobbies. To be sure they get adequate representation of their customer base, they divide their customers into groups. You know, those who do a lot of hiking, those who are swimmers, and so on. Then he randomly selects a certain number of customers in each group to survey. What are you looking at here?
Systematic.
Well, it would be systematic if it was number 5, number 10, and number 15, but he's not doing
Stratified random.
Yes, I would go that one. And off we go. Right, now, there are lots of questions like that. Basically, you're going to read those definitions 2 or 3 times. You're going to read the story, and then you're going to try and figure out what features they have. Now, in a question like number 3, there is more than one correct answer, right? So explain the difference between a set-aside and a cluster, and here's your choices. That's just some more of the same. So who shall I pick? Let's pick some more stories then. We're going to use postal zip codes to divide the state into regions. Then we're going to pick 10 of those zip codes and then include all the businesses in that. So that's got a structure, right? Zip codes, 10 of them, and then everybody. The key word here is the everybody. What does that get you?
Is that a cluster sample?
That's the difference, right? If you ask everybody, it's a cluster. If you only ask some of them, it's much more likely to be stratified, right? So everybody is a cluster. If you only pick some of them, it's more likely to be stratified. E, group the businesses according to their type. Some are medical, some are retail, some are construction, and so on. Randomly select a sample of 10 businesses from each type.
Stratified.
That's a stratified, right? You're only picking 10 businesses from each of those subgroups. And a whole more of these. Hopefully by the time you get to the end of these, you'll be really good. So, time to move on. There is, remember, a whole load of stuff in the book where you can read over their descriptions of those types of samples as well. And that might help you. What we're going to look at now are some new terms. We're going to be looking at what are called experiments and observational studies. And we're going to look at experiments first. Right, an experiment is where you collect your information. A lot of scientists use the experimental method to collect their information. Doctors, pharmaceuticals, people who are studying diseases very often try, if they can, to use the experimental method as well. Basically, you get a random sample of typically two groups. One of the groups will be called the experimental group, and the other will be called the control group. And these two groups should be essentially the same as each other. So you like get 1,000 people and you randomly put them into two groups, right? 500 go into the control, 500 go into the experiment group. And then you do something to this group that you don't do to that group. So let's suppose we are interested in the effectiveness of a new headache pill, right? So what you do is that this group, let's say there's 500 in it, each of these get the real pill. And the control group, let's say there's 500 of them, they get a sugar pill. It's called a placebo. And you collect data on how many headaches did you get, right? So if you take this pill every day, you're not going to get as many headaches, right? That's what they're hoping their pill's going to show, right? So you do it for 6 months or whatever time you want, and you collect your data, and you find out that in this group, on average, they got about 2 headaches a month. And the one in this group, they were getting 5 headaches per month, right? So you meant to take this pill every day and it stops you, or at least it reduces how many headaches you get. Based on this data, isn't there good evidence that that pill is actually working? Don't you get less headaches when you take the pill than if you essentially don't take the pill? And that's great evidence, and that's the kind of thing that they would be using to advertise their headache pill. They say, look, instead of you taking a pill when you get a headache, why don't you take our new pill, which you just take once a day, and you'll have a lot less headaches than you used to get, right? It's a bit of like, you know that stuff you take before you eat spicy food so you don't get an upset stomach, rather than taking the stuff after you've got an upset stomach, right? It's that kind of idea. Now, let's talk about this thing called the placebo effect. The reason why this group had to be given a pill that looks just like this one is because of the placebo effect. Has anybody heard of that term before we get into the details? Anybody want to throw in what it means to them? What do you remember about the placebo effect?
Isn't it like you're pretty much given like a sugar pill and you think it's doing something, but it's really not the real thing?
Yeah. Your brain is a very pliable thing, and isn't pain, part of pain, very subjective, right? And it's been found that psychologically, if you take a pill and you believe that pill is going to do something, like maybe make your headache go away or whatever, it can very often have that effect. Not perfect, but it can have that effect. And it's called the placebo effect. And it was a pain in the butt when they found out about it, because if they didn't do that, the data got distorted because of it, right? Just giving them a pill, even if there was nothing in it, it would reduce your headaches if you thought it was going to do that as a job. Now, we have this thing called the single blind and this thing called the double blind. Let's tell you how that works. A single blind experiment is, well, let's rewind a little bit. Let's pretend it's you in charge of this, right? You've randomly split them into two groups. You've randomly decided this group's getting the pill, this guy's getting the sugar pill. You've done all that. Now you then are collecting the data. A single blind would be the person in each group. None of them know what kind of pill they're getting. Do you think it would defeat the purpose if we went and said to you, okay, guys, you're getting the painkiller pill, and say to this group, guys, we're just using you as a control. This is just a sugar pill. It's not going to do anything, but we have to give you it because, you know, we need a second group. Wouldn't that destroy the placebo effect as well? So you don't do that. You don't tell either of them. And if they don't know, it's called a single blind, right? So the people who are receiving the treatment, if they don't know which one they're in, control or experiment, that's called single blind. If, however, the doctor who's in charge of these people, because very often you go to your doctor like every month and the doctor will say how you keeping, any side effects, you know, how many headaches, you know, they collect all that data. If your doctor knows which pill you are getting, he can actually affect the results. Now, it's not that he turns to Zach and says, Zach, you know you're getting a sugar pill and that pill you're taking is totally useless. You know, they don't do that. But what they found is that when a doctor knows that you're getting a control or the treatment, that the way they interact with you subconsciously can actually affect you. Because I would do something like this. Let's suppose, Zach, I know you're not getting the good pill, and I know that you've been getting horrible headaches, right? That's why I put you in this, you know, I suggested you take part, right? And then you come in and I'm saying, how you feeling, Zach? How are those headaches? I mean, are you having a lot of them still? And, you know, because I know you're getting the sugar pill, wouldn't that might be the way I would be talking to you? And then you're going to pick that up, right? So we have what's called the double blind. The double blind is even your doctor doesn't know which pill you're getting. As far as your doctor's concerned, you could be getting the real pill, you could be getting the sugar pill. So when he interacts with Zach, you see he will interact with them without any bias, right? He won't be extra concerned for him or extra interested to see if the pill's working, right? And that is a very big deal. We try to always have a placebo effect if we can, and we try always to have a double blind. That is the perfect experiment, right? Because the data you get is unbiased, right? It's the pill that's doing it and nothing else. Pretty cool. Any of you going to be nurses? Right, that's your thing, Mackenzie, right?
PA, nursing.
You're going to find that a lot of the information that you're given in the medical world comes from experiments, right? People have done different ways and they come back to you. Because I think, or just off my top of the head, haven't they changed the way that they do mouth-to-mouth resuscitation over the last 20 years? The methods that they use have changed. Now, the way that they've done that is that they've looked into it, they've done experiments and figured out which techniques have actually give better results than others. If you go to major casualty hospitals, they have already changed things like if someone has a gunshot wound, the protocol of how you treat them has changed through time. They found out if you're shot in the chest that you should turn them so that the lung that's not shot is highest. So the blood will just run into one bad lung, not into both. So you don't have them flat on their back. You put them on their side, for instance. So all these types of things weren't just made up by somebody, right? They definitely went and said, okay, what's your protocol? Well, when they come in, we lie them on the back and we stick their thing in, we do this. What's your protocol? Oh, we run, you know, we turn them on the side. How many of yours lived? How many of theirs lived? More people lived when you did it this way than if you did it that way. And any new pill that comes on the market is almost always going to be done this way, so that any results that come through, you know, change in blood pressure, work good. Really, really valuable way of collecting data. Now, what does an observational study look like? Observational studies are nowhere near as good as experiments. The data you get isn't as reliable or as convincing as it would be with an experiment. An observational study can have all sorts of different ways of doing it. A simple one. Suppose you are interested in whether boys are more aggressive than girls. And we're talking kindergarten age, right? An observational study might simply be that you set up cameras in their playroom and you just, video the kids playing, and you count the number of aggressive interactions are, right? So if a boy throws a toy at somebody, right? If a boy, pushes someone, right? Whatever you decide is aggressive actions. And you count how many times a boy did this and how many times a girl did this. And that is an observational study, right? Do you see that you haven't split your people into two groups and said to one of them, go and hit each other and the other one don't, right? You haven't done anything to separate them. An observational study could be, couldn't you find two groups? One is non-smokers, people who do not smoke cannabis, and those who do smoke cannabis. Now, you don't pick the groups. In other words, you don't say you become a non-smoker and the next person you become a smoker. Aren't these people already decided what they're going to be, right? I don't smoke, I do. So you do have two groups, but it's not the same as these, right? Non-smokers, smokers. And let's say you get 200 of each. And what you do is that you just follow them for a year or 2 years or even 10 years. Sometimes it has to be long-term studies. And you find out the percentage of, let's say, mental illness. But how many of them had to go to a psychiatrist for anxiety, for depression, whatever it is. And let's suppose the non-smokers, it was 15%, had some kind of issue, right? I'm not talking, crazy issue, right? Just some kind of mental health issues, as almost everybody at some time in their life will probably experience. And this is made up numbers. The cannabis smokers are 25% of them over a 10-year period ended up at least sometime in their life needing some help on anxiety, depression, whatever. And 15% of the non-smokers. Now, you might look at that data and say, well, yeah, cannabis smoking is bad for your mental health. It's much higher for the cannabis smokers than it is for the non-smokers. But that might not be the real reason these two numbers are different. Here's a totally made up explanation, but it could be true. Couldn't cannabis smokers be cannabis smokers because they're already quite anxious people and smoking cannabis calms them down? It's like self-medication. Well, because more of them are anxious, doesn't it seem reasonable that 25% of them are probably going to have to get some kind of help sometime in their life, right? For depression or anxiety. Couldn't that be the only reason between these? And non-smokers are less stressed out and therefore don't need cannabis to chill out. And that's not all of them, but couldn't that be enough of them to make a difference? So you see, you can't tell why the difference is happening because couldn't it be some other reason? That's why observations are so difficult to use as good evidence. And we even have a name for things. We call them confounding factors. A confounding factor is another reason for why these two groups are different. Now, if you wanted to get evidence on mental health and long-term cannabis smoking, you'd have to be in Nazi Germany to do it. What you'd have to do is get 400 people, right, general population, put them into 2 groups of 200 and say to this group, you're never, ever going to smoke cannabis or we'll shoot you, right? You're going to jail. We'll do horrible things to you. And you say to these guys, you're going to smoke 50, whatever it is, cannabis cigarettes a day for the next 10 years. And you're not allowed to not do it or we'll shoot you or put you in jail or do something bad to you. Now, since the 2 groups started off as being pretty much homogeneous, right? They're all the same kind of people, and you just randomly put them into 2, wouldn't the only difference at the end of 10 years be what the cannabis did to them mentally? Because these would be old and young, stressed and not stressed, fat and skinny and everything else under the sun, right? They're pretty much the same group. And the only thing that was different is about taking them. Now, for lots of very good reasons, that's not allowed. Agreed? You cannot do that to people. It has been, unfortunately, true that this method of converting it to an experiment has been done. Nazi Germany did an awful lot of really, really horrible experiments to people in concentration camps, and they used this scientific method to get that data. And there was a big, it's gone now because that data's irrelevant, but there was a big problem at the end of the Second World War. If you want to, you should read it up, where a lot of the, like Russia and Germany and Britain and America got the data that they got. Because, for instance, they did things like put people under extreme cold to see what it would happen to their bodies, right? And they'd done some really horrible things. And then the bottom line is, should you use the data that they got? Because it was really good. And that's the problem, isn't it? A lot of people were saying, no, that you should never use that data. That data came from horrible things that were done to people. It should never be used. And then there was another group of people said, yeah, I would totally agree with you, but this data could save lives. This data would help us how to save person who had hypothermia, right? If you fall into ice, how did the Germans, the Nazis, revive some of the patients and they lived, right? What did they do, right? What kind of numbers tell you something? Really horrible. I'm on the side you should never do it. But you can imagine there might be people who had, what's that horrible phrase that I dislike? The ends justify the means. I hate that. No, the ends do not justify the means, in my opinion. But some countries, and I'm going to pick on them because I can, Russia used a lot of that data. Stalin really didn't care where it came from. He used it. Okay, that was a kind of depressing story, wasn't it? So let's move on. So we are looking now at observational study or an experiment. And I'm going to show you just an example of what that question would look like. They're very wordy. So here we go. Which technique, observational study or experiment, do you think was used in the following? So the first one was, the Colorado Division of Wildlife netted and released 774 fish at this reservoir. There were 219 perch, 315 bluegill, 83 pike, and 157 rainbow trout. So I guess they just found out roughly what percentage of each of the kinds of fish that live in that lake. And they give you 2 reasons why it's experimental and 2 reasons why it's observational. So they're going to be called 1, 2, 3, and 4. Now, since you get 5 guesses, aren't you eventually going to get the right answer? But we're going to try and see if we can figure out whether this was observational or whether this was experimental. What do you think? Observational or experimental?
Would it be observational?
I would go with observational. Would you agree they just pulled the fish out the water and they looked at them? They kind of observed them. there's no indication here, is there, of two separate groups? Would you agree? Don't you need two separate groups for an experiment? So that would be my one. Now, there are two ones. You have this guy and you have this guy. So let's see which one of them it is. The second dot, this one here, it's an observational study because a treatment was deliberately imposed on them. No, it wasn't. This is an observational study because observations and measures are conducted in a way that doesn't change the response variable. I wish they'd phrased it less like a lawyer, but that's the one, right? No particular reason, let's pick this one. An ecology class uses binoculars to watch 23 turtles at Lowell Ponds. And they found that 18 of them, oh, well, I'm not going to spend a lot of time on that now. I've started the question. Would you agree that's observational? Right. So let's see if I can find an experiment. Right. They caught 41 bighorn. They gave an injection to prevent heartworm. And then later on, they measured them. That is an experiment, but it's not got, well, it's got a before and an after. So I guess it has two groups, right? They caught them, injected them, and then they found out what happened later. Oh, here we go. A study of all league football scores attained through touchdowns and field goals was conducted by the National Football Association to determine whether field goals account for more scoring events than touchdowns. So they actually got every single game that was played and how the points were made up, right? They got so many from field goals and so on. And we have a sample, an experiment, a simulation, or a census. What do you call it when you collect everything? Because that's really what this is. That you get all the data. There's no sampling. You looked at everybody.
A census?
It's called a census. Let's pick B. The effect of wind shear on airplanes during both landing and takeoff were studied by using a complex computer program to simulate it or to mimic it. It's called a simulation. Do you know that simulations are used heavily in things like weather forecasts? Right? They've got models that represent what, you know, the weather does. And they just put in information like, right now there's a hurricane, this is where it is, this is its velocity, this is it, you know, they put in all the data they can. And then the simulation says, oh, this hurricane is going to go and do that. And then you try and warn people a couple of days ahead, you know, this hurricane's coming and it's probably going to hit landfall here and it's probably going to be a force 8, whatever the numbers are. Now, I'll let you read those ones because they have their own things. And that's the end of that one. So we are now going to move on to a new section. Now, yes. Any questions, sorry, before we continue? There are going to be a lot of things that you're going to have to read up again, right? There are going to be little nuances, and that's part of the learning process. So bear that in mind. I'm trying to load this next thing up, and it's not wanting to because I'm having one of those days. So while we're getting that, I'll show you the next topic. We are going to be looking at chapter 3. In chapter 3 is frequency tables and histograms. So let's assume that we've collected good data, right? We've done a sample, it's a simple random sample, whatever it might be, and we now have some data. And what we want to do is try and put it in a form that makes it easier to see what's going on. Now, if I just gave you a big list of numbers, I don't think you'd be able to see much. Let's suppose we collected data on how many children were in families, right? So we had 5, we had 7, we had 1. There was just 1 child in a family, 2 children, no children, 7, and so on. Would you agree if I gave you 100 numbers in a big list like that and saying, hey, I've collected the data you wanted? Can you imagine what your boss would say? What the heck am I going to do with 100 numbers that look like that? I can't tell anything. Would you agree there's nothing obvious going on? And wouldn't it be nice if we could put it in a format that would make it easier to see what was going on? And I'm still having trouble loading that guy up. So if you bear with me for a second, I think it's up and running now. So how would you take this data and make it so that it was easier to see? So we're going to look at frequency tables first, and then we'll move on and look at some other situations. Well, one type of frequency table would look like this. You would put a column, number of children in the family. And then you'd have a second column, which you would call the frequency. And you would probably get software to do it, but you'd go 0, 1, 2. So these are married couples. And you found out that 15 of them didn't have any children, 39, 51, 20, 15, 10, nobody with 6, 10, 20, 30, 40, 50, 60, 10. And for some reason, 10 down here, right? Pretty unreasonable, but I wanted a nice round number. 14, 15, 20, 0, 3, 4, 5, 6, 7, 12, 13, 14, 15, 16. So my sample consisted of 160 parents. And this data is now in the form of a table. Can you see that it's a little bit easier to see what's going on? For instance, if I went and said to you, what's the most common number of children in a family? You would say, oh, having 2 children in your family is the most common, and 51 out of 160 of them, right, fell into that category. If I said to you, what was the least common size, you would say, very few have 6 children in the family, right? Nobody in this case. Even although that was 0, do you notice you still put the number in? You don't just go 5, 7 and forget about the missing numbers. When you do a frequency table, zeros are important, right? So all the numbers, including 6, go here. Now, if you look at these numbers, isn't there a sort of a pattern going on? Doesn't it start off small, get bigger, and then drift away a little bit? So I can see that. There is sometimes an extra column. And this extra column is called the relative frequency. And the way you get the relative frequency is basically you take 15 and divide it by the total number. So you would go 15 divided by 160, and you'd get approximately 0.09. And then you do 39 divided by 160, and you'd get 0.24. And then 51 divided by 160, and you get 0.32. And as I go through each of them, I'll call that one 3. And the relative frequency is very often going to be a decimal. Less common, but it is sometimes done, is that the relative frequency might be given as a percentage. Now, suppose you were doing a calculation as I just did by hand. What would you expect to get if you add up all these relative frequencies in decimals? What total would you expect to get? What number?
100.
On the percentages, 100%. And on the decimal side, wouldn't you expect 1.00? Now, if the numbers weren't rounded off, you would get 1.00. Because you sometimes, by practical purposes, don't you have to round off somewhere, right? You can't just write down 22 digits every time. Well, couldn't there be a little bit of rounding off error? So you might get 1.01, 0.98, and that's okay, because that's just rounding off. And the same thing here, couldn't this be 101% or 99%? And it's just caused by some of them were rounded up and others were rounded down. But in general, in a perfect world, 1 and 100%. And that's what a frequency table looks like. You put the data in order, you count how many things were equal to whatever that data is, turn it into a decimal or a percentage to get the relative frequency. Now, if you want to create a histogram, it will look something like this. Along the bottom, you would put whatever the label is. In this case, it's the number of children in the family. And then vertically, you put frequency. In this case, it's 0, 1, 2, 3, 4, 5, 6, and finally 7. Oh, just made it. Do you remember doing things like this in high school? It takes forever and a day, doesn't it? The cool news is I'll show you how Salt does it for you, but I just want to show you it by hand once, and then we'll let the software do it in the future. So I need to go as far up as 51. So there we go. So it's going to be 10, 20, 30, 40, and 50. So the first group was 15, so it's about here. Then the next one was 39, so it's just a touch shy. And the next one is 51, so that's about here. And the next one is 20, which takes me to about here. And the next one is 15, which is about here. Then I get 10, which is about here. Then I don't have anybody. And then I get 10 again. Does that look kind of familiar? Go to histogram. Are we good? Now, histogram. What other kind of shapes can we have? Well, we can have other things, there's a guy called a box plot. There's a guy called a pie chart. And there's a guy, sometimes you use a scatter plot. A box plot. Have you ever seen a guy that looks like this? Ever seen that shape? That's a box plot. You ever seen a pie chart? Looks like that, right? Scatter plot. Instead of doing rectangles, you basically do, you know, points. You may or may not join them together. Probably you shouldn't join them. So if I was doing this one a little bit more accurately, it would look something much more like this. Right. Each one of those dots represents that height. And this would be 0, 1, 2, 3, 4, you know, going along the bottom. So there are a number of different visual ways you can take your raw data, turn it into a frequency table, and then that frequency table can then become a histogram or a box plot or a pie chart or a scatter plot. And it's nice if someone else will do the work for us. Agreed? So let me see if I can show you how Salt does this. Come on, I want Salt. There we are. Now that does do Salt. Is there any more than just that one? No, okay. I'll just use this one here. Now, here is the raw data. We are not going to count every number separately, because if we did that, we'd have a huge big table with only 154, 255s, no 56s, right? So what you do is you're going to group the data, and here are what they're calling the class boundaries, right? So I'm going to have to write them down or I'll forget what they are. But it's 53.5 and the next number is 99.5. So any number that is in the range 53.5 to 99.5 gets kind of put together as one clump. So if I wanted to know that number, let's see who would work. 1, 2, 3, 4, 5, actually, wouldn't it be all those numbers there? So it's a very ugly looking histogram, but nonetheless, I'll do it. So I'm going to use Salt. Now, there we go. Are you looking at all those numbers? You see them here? You can scroll all the way down to the end, right? And we would like to do a histogram. Charts and graphs. Histogram. Select the variable salary. Right. That's good. Now we want to do, where do we start? We start at 53.5. And what they're calling is the bin or the class width was the start to the finish of that first group, which you can't see anymore. But if you take 99.5 and subtract 53.5, you're left with 46. And recalculate the graph. And it's a very boring graph. You see, there we go. It's got a huge big rectangle and then a little baby one at the end. And that would be it. I wish they had a better data set here. So I am going to cheat and do this question again. But okay, by the way, the answer that we got was one of these two guys, wasn't it? And it happens to be this one. But I'm going to hit this again. And as I said, I'm going to cheat quite a bit here. First thing I'm going to do is I'm going to get rid of that last digit. There, boom. So see that 200 guy, he's gone. You see that? Now, I'm going to go and do a different histogram. So charts and graphs, histogram. I'm going to make it, that's the salary. Oh, that was nice of them. And do you see they started at 54 for me and did bin sizes 11? I'm going to do bin sizes of 10 and I'm going to recalculate it. There, can you see our histogram? Already done for us. Now, the way that you kind of measure your histogram is 54 to that number there, right? So it would be 54 to 64, right? So that would be 54 to 64. Let me cheat a little bit just to make this easier. Let's start at 50. There, recalculate again. There, isn't it a little bit easier now to see the groups? Can you see anybody between 50 and 60 is in this group? There's 6 of them. The 60 to 70s, the 70 to 80s, and there is your histogram. I would like a, what else would I like? I would like a box plot. There we go. There's your box plot. You don't need to tell it. A box plot has fixed structure. You see, it's turned vertically, but that's a box plot. I would like a scatter plot. Oh, I can't do a scatter plot because there's only one variable here. I would like a pie chart. Why can't I do? Pie chart can be created because a categorical variable is not defined within the data. Okay, that particular one wasn't lending itself to a pie chart, so that's fine. Not all data fits into a single method. So you can do all those things without actually doing them by hand. You're going to do pie charts when it's a table. Can you imagine somebody said, what's your favorite color? And 8 said red and 17 said blue and 11 said green. Wouldn't that work really well with a pie chart? Right, certain data works better with certain circumstances. So let's move on and talk about the shape of histograms. We have a vocabulary that we use to describe the shapes that you get in histograms. Now, normally, if I had time, I would draw a histogram with lots of little rectangles, but they take too long to do. So if I just draw that, can you imagine that's just a short version of this shape, right? So we're really interested in what the shape of a histogram is. Now, one of the common shapes you get is, do you see this single hill, nice symmetric shape? This guy. We call this symmetric. We also call it bell-shaped, because it does look a little bit like a bell, doesn't it? And we also have a third name for it. It's sometimes called normal distribution. Now, can you imagine that you got data that looked like that? Now, it's not symmetric. Do you see that it looks kind of symmetric, but isn't it got a long right-hand side set of data, right? It kind of trails off for a long way. When you have a shape like that, we call it skewed to the right, or in some textbooks, we call it right skewed. And it shouldn't require too much imagination. What do you think data that looks like that, it's going to be called.
Skew to the left.
Correct. Or sometimes left. Skewed. We even have a name for this piece here. See this little guy in here? This little guy here. If you were going to invent a name for the piece of the curve that's here, the piece of the data's here, make up a name and see if you got lucky. What might you call this guy?
Tail.
Yes, it is. It's called a tail. Do you know what this piece is called? If you were making up a name, what would you call this bit?
Apex.
Now, one of the uses of having labels or names to shapes is that it means that we can describe something using words without having to show you the picture. So if I went and, well, let me add one more thing before I do that. There is a thing called an outlier. And that is essentially an extreme data point. That is somebody who's really, really big and not like any of the other numbers, or really, really small. So imagine I had data that was the ages of people in a chess club. And it looked like that, right? Can you see that everybody, I don't know, everybody is from 10 to say 50, right? Isn't pretty much all the data 10 to 50-year-olds? And you've got your great grandfather who plays chess and he's in the club and he's 99. He is considered an outlier. Does that make sense what an outlier looks like? Outliers can happen for lots of reasons. They could happen because he's just exceptionally old, right? And that's true, yes, and that's fine. When I did that histogram the first time, didn't it look really ugly when we kept the 200 in? It was one big rectangle, a big gap and a single guy. Wasn't it nicer when I took it away? So very often outliers distort the shape, right? It's hard to see the shape if this outlier is really big, because what you might end up getting is basically this, right? And you can't really tell what's going on. And so you might have to destroy an outlier just to see what shape is happening, what most of the data looks like. Of course, you can have an outlier away over here. Can you have two outliers? Yeah. Maybe his wife also plays chess and she's 100. Wouldn't both of those be outliers? Right? It's not like there can only be one outlier. Can't there be 2, 3 outliers? We good? Right. Now, suppose I said to you that I had some data it was skewed to the left and it had one large outlier. So I've only told you what it looks like by using the jargon of today. If you were trying to sketch what that might look like, there is actually enough information here to get a rough guide. It's skewed to the left. So shouldn't it look like that? And one very large outlier. Would you agree that's maybe what you were visualizing? Right? Skewed to the left. See your little tail? Skewed to the left. And one extreme large outlier. Any questions so far? Are you comfortable about how to name histograms and what an outlier would look like, and how, if someone said describe a particular histogram, you could do it? Okay, let's put you in on the spot then. Describe that histogram.
Would be skewed to the right with one large outlier.
I would disagree with you on part of what you said. I like the outlier.
Normal.
If you make the outlier go away, and maybe it's the way I've drawn it, right? Pretend the outlier's not there. What do you see now?
It's normal.
Right, symmetric, normal, right? Whatever. So I would describe this as symmetric with one extremely large outlier. That would be the phrase I would use. So the outlier does distract you, doesn't it? Because it tends to make you make the tail go. But the good thing is, if you think something's an outlier, if you cover it up, doesn't your brain refocus and you see the shape better? Right, that's how you should decide what the general shape is. So let's return, to my relative frequency table, this guy here. And I'm now going to add, and I wish I'd planned this ahead, but I didn't. I'm going to add yet another column. And this final column is called the cumulative frequency. So I'm going to bend these two guys out the way because they're a distraction and put this guy back. Now, how does cumulative frequency get calculated? Let's see. First one, 15. The second one is add those two together, you get 54. The next one, you add these three together, 105. The next one, you add all four together, you get 125. You add the next guy, you get 140. You add the next guy, you get 150. You add the next guy, it's still 150. And finally, you finish by adding all of them together and you get 160. Do you see how I created what was called the cumulative frequency? 15. Add the first two together. Add the first three together. Add all of them together. That is called a cumulative frequency table. So for instance, I can tell you that if we look at no children up to 5, 150 parents have a family size with none up to 5 children. I can tell you that if you go to 3 children, there's 125 parents who have 3 or less children in their family. So you see, this table allows you to answer questions like that relatively easily because the numbers you need are there. That makes sense? Now, what do you typically, or how do you typically draw that as a picture? Well, you would, along the x-axis, you would do number of children. And you could do histograms, right? So you could go 0, 1, 2, 3, 4, 5, and so on. Actually, I might put 0 there. 1, 2, 3, 4, 5, 6, 7. And you would do, I'll have to do a scale here, I need 160. Okay. 0, that was 15, so if that's 20, 15 is about here. 1, it was 39, which is about here. 2 is 51, which is about here. 3 children, oh yeah. made a mistake. Let's start again. 0 is 15. Cover you up. Right. 0 is 15. 1 is 54. So I'm going to have to go here for 54. Here. So we'll join them. There you go. 2 is 105, which is about here. 3 is 125, which is about here. 4 is 140, which is here. 5 is 150, which is about here. 6 is 150, which is same place. And 7 would be here. And there is a cumulative frequency diagram. These are called Ojai curves. So Ojai curves are cumulative frequency curves, where along the bottom you put the number of children and vertically you put the cumulative frequency values. If you look at this chart, would you agree that it is increasing quite steeply at the beginning, and then isn't it just, well, maybe not leveling off, but isn't it less curved, less steep? And what that is telling us that at the beginning, most of the children, most of the big numbers live, right? Most of the family sizes are in this stage here. Are we good? Let's show you some homework questions. Done that for a while. Right, here we have the Ojais are based on US data and show the average annual personal income per capita in each of the 50 states.
I don't think I'm seeing what you're saying.
Oh, okay, let me try that again. Thank you for telling me that. There, are you seeing it now?
Yeah.
So in this part of the world, personal income per capita per state. Okay. So if you look at 27.50, right? Okay. If you're looking at about 37,500, that's about what, 36 states out of 50 have that as their average income or less. I guess that's how you would read it. Pretty boring one about whole numbers. And how's our time going? I think we're not going to make it. We are not. But it was perfect timing. It's 11:25. So will you make sure that you put your last name down for attendance? Before I forget, tomorrow's kind of special. Today you will get your video up on Canvas as usual, probably about 7 o'clock in the evening. No biggie, right? That's where it's always going to be. Tomorrow's special, me and my wife are off to Vegas. Yay! So I'm going to get drunk and start a fight and run away. Oh, even better. No, I'm not allowed to do that according to my wife, so I won't. But I will get to go to our favourite casino and lose lots of money, as I typically do.
Which
But
casino is that?
We like to go to a place called the Tuscany Inn and Suites. It's
Nice.
off the main. So if I see you there, I'm going to give you into a row because you should be studying and doing your homework.
Of course, of course.
Okay. So anyway, the bottom line is that you won't be able to get a video tomorrow because it takes about an hour for the video to be downloaded. And then I have to spend about an hour, half an hour fixing it. And then I have to upload it. And I won't be here. I'll be on a plane. So you're going to have to just take a lot of notes. for Thursday, right? That's the only advice I can give you. I'm trying to figure out a way of making Pinamp to record the videos so you can just go there. But for the life of me, it ain't working. I tried it and I don't know why it's not doing it. If I get that fixed, I'll tell you tomorrow. So, you know, homework this Sunday is going to conclude everything up to we get finished tomorrow, which hopefully should be, you know, what's on my list. And when I see you on Monday and I've got a black eye and no money, you'll know why. Okay. None of you believe I would drink and start a fight, right? You know I'm joking. Okay, good. So last name and bye-byes, and I will see you tomorrow.